Rabab Haider's PhD Defense. Rabab finished her bachelor's from the University of Toronto and came to MIT in 2018. Joined our lab and finished her master's in 2020. And today she's here to defend her thesis work on physics-aware optimization and data-driven methods for low-carbon power systems. She has written a number of papers, both journal and conferences, won a number of awards, a number of fellowships. And so it's a sort of a very bittersweet thing for me here to see that it's all, coming to an end. But I'm sure this is only the beginning of even better things for her. So she'll present her research for about 40-45 minutes or so. And then we open it up for general questions from the audience and then from the committee. And Dr. Haider is on Zoom, and so we'll ask questions. And then after that, if you're all going to step out and the committee deliberates, any faculty who's present can stay here, but I don't know if anybody's on Zoom. But in any case, and then we conclude everything. And hoping it all goes well, there's a little party upstairs in B434, so 434 building 3 for a small celebration. So please do to join. So without any further ado, Rabab, the floor is yours.
Thank you. Thank you so much for the introduction. And thank you everyone for being here. If anytime on the Zoom, if I can't be audible, please let me know. And then if you could ping me if it's hard to hear me, I'll do my best to talk loudly. So as Dr. Swami introduced, my name is Rabab Haider, and today I'm defending my thesis titled Physics-Aware Optimization and Data-Driven Methods for Low-Carbon Power Systems. So before I get started, I want to pose, let's see, sorry, is my screen share on? Yes, but I don't see it on my side. Sorry, brief technical difficulties. Okay, you can see the screen. Okay, sorry about that. So before I get started, I want to pose a question to you. How do we reliably keep lights on in a low carbon energy future? So this is the central question that I'm tackling in my thesis. So to understand what I'm talking about, as we're moving towards 100% carbon-free electricity and working towards our climate goals, we have to reimagine how the electricity system today works. Today, generators will produce electricity, which is then transported through the transmission and distribution system down to customers with their load. So suppose you have a laptop that you need to charge, you're going to plug that device in, and the demand that you request will be balanced in real time by supply, by the generation. And so this balancing of supply and demand in real time is a central challenge to power systems operations. The challenge with 100% carbon-free electricity is that the resources we're looking at, wind and solar, are intermittent resources. This means that they change rapidly in generation. So imagine the wind stops blowing or a cloud moves over the sun. And further, they're only available when those resources are available. So when the sun is shining or the wind is blowing. In order to achieve 100% carbon-free electricity and still meet all of the demand, one thing you could think of is storage. So we could just store all the energy, charge up our batteries, and discharge when those resources are no longer available. But grid scale and grid-wide storage is still very expensive to realize. And so we need to find flexibility elsewhere in the electricity system in order to achieve 100% carbon-free electricity. And so this flexibility has to be at fast timescales, similar to the timescales on the generation side. And we can look towards distributed energy resources, or DERs, to provide some of this flexibility. This includes things like electric vehicles, rooftop solar, or smart loads like a smart thermostat or a flexible load. And so these resources can provide the flexibility we need in order to achieve reliable system operation. And so towards this goal of reliability with 100% carbon-free electricity, my approach is to propose flexible and dynamic decision-making mechanisms. And I've worked on a number of different projects, if you can see over here, that address this challenge. For the sake of time, I'm going to focus on chapters 3 and 4, which are targeting how to keep lights on efficiently and in a steady manner. This is the outline of my talk today. So for that first part, how do we efficiently keep lights on in a low carbon energy future? One approach is that of dynamic grid reconfiguration. So to explain what this looks like, suppose we have a large load in the distribution system. And when local resources like solar aren't available, that load will be met by the large scale generators from the transmission system. However, later in the day when solar becomes available, it makes sense to connect that resource directly to that large load. And this reconfiguration of the grid topology requires the turning on and off of different switches in the network. And so making this decision on when and which switches to turn on and off in order to connect that load with that clean generation and to do that efficiently can be cast as an optimization problem as follows. So our objective is to minimize line losses, which is a proxy for how efficiently the grid operates. And we're subject to three sets of constraints. The first is our power physics. These include things like generalized Ohm's law. It includes power balance, which is like an energy balance, and voltage limits. So we want to maintain voltage limits in the grid throughout all of our operations. The challenge here is that these power physics, when they are violated, the optimization solution proposed by the solver isn't realizable. And so they impose hard constraints on the system. The second set of constraints come from our grid topology constraints, and these are operational requirements of distribution grid. So the first is connectivity, and that means that at any given time, when we're in normal operating structures, all the nodes in the network have to be connected to the larger grid. And the second is radiality, where we want a roughly tree-like structure in the distribution system. The last set of constraints come from our devices. And so this would be things like solar generation forecasts. And if you have other devices like storage or flexible loads, it would also include their models as well. So the distribution grid reconfiguration problem is trying to simultaneously optimize the grid topology and the resource dispatch in order to meet electricity demand and to do so in an efficient manner. And so the reconfiguration optimization has multiple challenges, however. So the first is that electricity is an essential service, and those hard constraints that we have from our power physics must be met at all times. We have to balance our demand, satisfy our demand and keep voltages within operating limits at all times. The second challenge is that the switches can either be on or off, and this means that we have binary variables or a combinatorial optimization problem. And this is challenging from an optimization perspective. The last challenge comes specifically from those distributed energy resources that are part of the modern distribution grid. So these solar resources are intermittent resources, and because the generation changes quickly, we have reduced timescales for decision making, and we have to make decisions in a faster manner. So the approaches taken in literature so far are all model-based approaches. And so they can include things like approximate solutions. However, a lot of these solutions require assumptions that the grid is passive. This means that there can't be solar generation. And so that assumption is voided in our modern distribution system. The second set of examples are heuristic optimization, but they don't have any performance guarantees. And the last is that we can use traditional optimization methods for mixed integer or combinatorial problems, but they're not dynamic, and these solvers typically don't converge quickly enough for our dynamic applications where we want to make decisions very quickly. And so my proposal is instead to fuse the optimal and feasible guarantees from model-based approaches with the speed of data-driven methods like neural networks. This domain is called physics-informed learning, and it's the idea that we use a knowledge of the physics and the underlying models in our system and fuse that with our machine learning algorithms in order to get good performance and fast performance for dynamic reconfiguration. To this end, I've proposed Grid Cipher, which is a end-to-end learning to optimize framework for the grid reconfiguration problem. So if we imagine that we have a combinatorial or mixed integer optimization problem, we have the following objective function subject to equality and inequality constraints, and just stressing that this variable space is composed of both continuous and discrete or integer variables. So we can just decompose the variable space into three. The first would be training data X, and then Z and Phi are independent and dependent variables, and these labels will become clear shortly. From a machine learning perspective, what we want to do is we want to have this training data, and we want to be able to train on this training data and then predict Z and Phi as the neural prediction. And so there are three key challenges that come from having this setup. Is that we have inequality constraints, equality constraints, and binary variables within this architecture. So the first challenge of inequality constraints, we can take a physics-informed approach to this, and we can simply penalize the value here. So what this looks like is anytime there is an inequality constraint violation, the value of the loss function goes up and is penalized over here. For the equality constraints, we can similarly take a physics-informed approach, and this is using techniques in variable space reduction. So if you imagine that you have an equality constraint, a plus b is equal to 1. If you know the value of a, you can calculate the value of b. And this is basically the idea behind variable space reduction. Here we can use our power physics, which are those hard limits, those equality constraints. And rather than having the neural network predict both z and phi, it will predict z, and then we can calculate phi from those equations. Now, this kind of approach has been done in literature and different applications before, but what has never been considered is the presence of those binary variables. And this makes optimization challenging. It makes machine learning also challenging in this type of framework. And so for this, I'm proposing the use of physics-informed rounding. And this approach is basically in embedding the physics that we know and the constraints on our binary variables within this architecture. And by embedding the physics specifically within this neural framework, we have certified satisfiability. That means that any prediction from our neural network is going to satisfy the binary constraints that we have, as well as the hard constraints on the power physics. And so we're always going to satisfy these. If we put this entire architecture together and apply to the grid reconfiguration problem, we will train on the load data, which we know and we need to serve this load in our grid. Then we are looking at the topology selection first. We have a switch on-off probability that's predicted by the neural network. Based on those probabilities, the physics-informed rounding is going to make a topology decision by deciding which switches are on or off. Now that we fixed the topology, we can now enforce the power physics upon that topology. The way we do that is we know the loads in the network, we predict the voltages, and that roughly gives us enough information to calculate the real and reactive power generation dispatched throughout the entire grid. At this point, we have all the information we need in order to calculate our loss function, which includes the penalty on the inequality constraints. And then we can go through the back propagation as we would typically do in a machine learning framework. So if we're looking at the dynamic reconfiguration, that particular decision on the switch statuses is very important. So the physics-informed rounding that I'm proposing is as follows. If we consider a distribution grid over here, it has 4 different nodes, which are the circles, and then 5 possible edges, and all of these have switches. In order for this structure to be radial, a necessary condition is that there are n-1 branches connecting all the nodes. So here we have n is equal to 4, which means we can only have 3 branches connecting the nodes. So we can only have 3 switches that are closed. The remaining 2 switches have to be open. Using this information and this physical requirement on the grid, we can construct a rounding function. The rounding function basically says that 3 switches are closed, and so we have power flowing through them, and then 2 are open, no power flowing through them. So if our neural network gives us an on-off probability for every switch in the network, we can then sort these probabilities. So the 3 switches with the largest probabilities get turned on, and the remaining 2 are off, and that gives us our full topology decision. And if we put it together with the rest of the framework, we can generalize to any distribution grid topology. As long as we know the topology, we know the number of nodes, we know the number of switches and the number of lines, we can calculate and design this rounding function. Similarly, for other optimization problems that have a similar structure where we can define this rounding function a priori, the same architecture can be used. So to give a bit more detail on this gray and the blue box over here, first, with the power physics, I'm using a linearized disk flow model. This is a very commonly used model in distribution system modeling. And we've expanded to include a big M relaxation. So this basically means as the topology of the network changes, the equations that we have can still fully describe the physics of the topology on the underlying grid. On the neural network side, I'm using a very simple neural network. It's just 2 fully hidden connected layers, ReLU activation, batch normalization. This is very typical in machine learning, and it's a very lightweight network. So what we're doing is we're keeping a very lightweight, simple architecture here, but we're embedding the physics in a very intelligent way in order to have both certified satisfiability and improved training performance and prediction performance. And we're gonna see this in the results. So now that I have this grid cipher architecture for making this decision, we can consider the application of dynamic reconfiguration in power systems. So first, I'm considering this canonical 33-node network. It has 33 nodes and 8 switches, and the 8 switches are those yellow lines here. Green lines, pardon me. And in this network, I've also introduced solar generation throughout, and that's denoted by the yellow squares in the network. This network's a really good test case for reconfiguration because it's a very lossy network. So there's a lot of line losses. And so if we're trying to minimize line losses, it's a good test case. And because it's very lossy, it also frequently violates the voltage limits in the network. So if we apply dynamic reconfiguration to this network, the ideal shape that we want to see is this ice cream cone. And we want to see a lot of the area up top where we see 1. And we want the entire area to be above that line of 0.95. And that's the lower limit for operating the grid in North America. So if we look at the results of the violin plot here, I also want to highlight that the width over here means that there are about that many different voltage measurements at that particular voltage level that we measured over this entire year of simulations. So in our violin plot, without reconfiguration, which is when we use the default topology as is and all of these switches are open, we see that we frequently violate the voltage limits. And so more than half of the time, the voltages are violated. This means that just having this network isn't enough, and the utility operator would need additional devices to boost all of those voltages above that 0.95 line. If we consider static reconfiguration, we see a significant improvement where a lot of this area is now above that line. And static reconfiguration is basically choosing one optimal topology for a very long time frame, in this case for an entire year. And it could be taking a robust optimization approach. When we move towards dynamic reconfiguration, we see additional improvements. So 82% of the voltages are within acceptable bounds. And this is the approach that I am suggesting we use of dynamic reconfiguration. And in these simulations, optimization was done every hour. So if the topology needed to change, it would be changed hourly as needed. In addition to improving the voltages, so having 66% fewer voltage violations, we also see 28% lower losses when we compare dynamic reconfiguration with no reconfiguration. And to put into perspective what this 28% means, it's enough energy to power 30 US households for an entire year. And this isn't by adding new generation, it's simply by making the grid more efficient by changing the underlying topology. So next I scaled up the simulations, and now I'm looking at a 94 node network. And this is a model of a real distribution grid in Taiwan. So this network has 14 switches, once again denoted by the green, and I've introduced solar once again by these yellow squares. This distribution network is a really good example for dynamic reconfiguration as well, because it has 11 individual distribution feeders. And these different distribution feeders denoted by the letters A through K, they can connect to one another through these lines and closing and opening these switches. So what happens is when we're looking at a lot of solar penetration, feeder F in particular might have overgeneration during some periods when the sun is shining, and it can then export power to neighboring feeders like feeder F or up to feeder B. And this allows these different feeders to power share and use the local generation more effectively. And so the simulation results do exactly that. We see that solar generation is used much more efficiently. If we consider a particular day of operation, the network is in what's called configuration 9. The highlight here is that feeder G is not connected to the rest of the network. It's able to serve its load with its local imports. But the rest of the feeders are connected, and they're basically transporting power, say, from feeder B to feeder I in this direction, that much power. Of the same day, when solar now becomes available at noon, we see that feeder G is now connected to the rest of the network, and it's actually exporting power. In this case, that power actually goes all the way down to feeder A. And this is because we now have a considerable amount of generation happening locally. And so that power is now being able to be exported and used throughout the network. While the direction of power flow doesn't change throughout all of these switches, we do see that the amount of power decreases. So we see 820 and now it's 671, and this is the same across all of these feeders. So what's happening is that each of these individual feeders are better able to use the local generation. They're able to reduce how much power is exported and overall increase the amount of solar generation that's used network-wide. And so if we compare dynamic reconfiguration with static reconfiguration, we see a 17% improvement and less solar is curtailed. And once again, this is about enough power to power 23 US households for an entire year of operation. I once again want to stress that this isn't by adding new resources. We haven't invested in more solar or added more generation facilities. We're just better using what's already there and curtailing less of those resources. And we're doing so in an efficient manner to reduce line losses. So now that I've hopefully convinced you that dynamic reconfiguration is a good pitch for power systems, I want to talk about how my proposed method to enable dynamic reconfiguration performs. To do so, I'm introducing a set of performance metrics, and I'm going to explain what they look like on this diagram over here. So suppose we have an optimization problem here, then this purple bean shape is the region where all of our equality and inequality constraints are satisfied. So that's our feasible region. And suppose we know the optimal value, and that is that X point. Our neural network may give us two different predictions, and those are the gray circles, psi1 and psi2. We see that psi1 is inside of that purple bean, which means it's a feasible solution, but it's not on top of that X, so it's not an optimal solution. And so we can calculate some distance to optimality. Similarly, psi2 has a distance to optimality, but it's outside of the purple shape, and so it also has a distance to feasibility. And so we can put metrics to this entire concept of optimality and feasibility. On the optimality side, we're really interested in whether we've asked the generators to produce the right amount of energy in both real and reactive power. And so we can measure the mean squared error of the dispatch solution. Similarly, we're interested in knowing if we've been able to predict the nodal voltage as well. And so we can get the mean squared error of the nodal voltages. The last error is looking at how optimal the topology is. And so the topology error is the ratio of switch decisions that are not in an optimal position. So if the topology error is 20%, it means 20% of the switches are not in their optimal position. However, every topology predicted by the grid cipher algorithm is feasible. So it's in that purple sphere, it just might not be optimal. And so we can still meet all of our loads with the generation that we have. The feasibility metrics are concerned with the inequality constraints. And I'm stressing once again that the equality constraints have certified satisfiability because they're embedded within our end-to-end learning framework. So for the inequality constraints, we can look at the mean and the maximum violation, as well as the number of violations that exceed a particular threshold. So to give you an example of what this looks like from a power perspective, suppose our neural network asks a particular solar generator to give us this yellow generation curve. However, what's actually available is this gray curve, and what's actually available is a yellow line. So anywhere where the gray curve that the neural networks requested is above the yellow curve of what's available, we have a violation of our inequality constraints. So we can calculate the mean violation and the maximum violation. And then this particular part that I have magnified where the yellow curve is above the gray, there are no violations here. And I just want to stress this is just a cartoon. So the neural network doesn't actually perform with this gray curve over here. So in order to test the proposed physics-informed routing algorithm, I've also designed and tested other architectures as well. The first is the INSI architecture, and it does not have the physics-informed rounding. Instead, what it's doing is it's using this continuous approximation to that 0-1 step function that you would imagine would be like a rounding function. And so while we're not able to enforce integer solutions, we're trying to promote integer solutions by using this integer sigmoid function. Next, I looked at a couple different architectures for our physics-informed rounding. So the output layer function of our neural network is a clamp. So we have Clapper, sigmoid cipher, which we'll see is the architecture that I've selected, and InCipher, which is using that integer sigmoid I introduced earlier. So all of these four architectures I've developed, tested, and then the results are presented as follows. So there are 7 key takeaways from the simulations that I run. And I want you to focus particularly that grid cipher enables high prediction accuracy. And we're going to see that again and again in the results. I'm not going to talk through all 7 of these right now, but I'll do it as I present the results. And I'm going to focus on the top 5 in the interest of time. So the first set of results are on that small network, the 33 node that was very lossy. The physics-informed methods are highlighted in blue. And just a reminder that this is an unsupervised training architecture. So the loss function we have is the line losses that we're trying to minimize in our optimization problem, and a penalty for violating our inequality constraints. And so the results look as follows. And the first thing we see is that there's this immediate trade-off between optimality and feasibility. So generally, when you see good performance as shown in green on the feasibility metric, you similarly see poor performance as shown in yellow on the optimality metrics. We also see that that FIR, and in particular, all of these 3 methods outperform INSI on all of the metrics. And so if we calculate the percentage error between the INSI prediction and the Clapper, for example, prediction, we see 12% lower error on dispatch metrics, 51% lower on the voltages, and significant improvement on the inequality constraints as well. I've also tested and trained and tested supervised methods. And so this is to understand how well we can actually do this end-to-end learning to optimize, as opposed to having full information of the optimal solution. So I have a supervised loss function that's just looking at those optimality metrics, and then another that's penalized with optimality metrics and a penalty for the inequality constraints. You can once again see that trade-off where we perform poorly on feasibility, but well on optimality, similarly to as before. What's really highlighted here is that the supervised learning performs really well on the optimality metrics, which is expected because it has full information of the optimal solution, but it does underperform on the feasibility metrics, in particular when there isn't a penalty in the loss function. When we do add the penalty in the loss function, we see performance that's actually comparable to the physics-informed rounding, particularly on the inequality constraint violations, which are really important. And this basically means that our end-to-end learning is able to compete with supervised learning without full optimal solution information. And this is particularly important because when we're training these neural networks, we might not actually have access to that kind of information. So we don't necessarily know the optimal solution for all of our training sets. So next, I looked at scaling up the neural network on the larger test case with 94 nodes, and also assessing how well it performs on unseen data distributions. And so I've trained this network on a data set that looks at perturbed loads, and this is very common in the literature. And I've tested once again on the same data set, but also on real residential load profiles, residential and commercial load profiles. And then this last data set is where the location or the size of the solar generators might be different in testing than they were in training. And this last test case is actually very relevant for utility companies because they have very little visibility into what's actually in their system. And so it's very likely that the data they have might not be the most accurate or up to date, and they might have new generators that are in the system. So the results look a little similar to what we have before, where once again, we see that the physics-informed method Cypher significantly outperforms InSci on all of my metrics that are shown here. We see that the FIR errors are almost 1,000 times lower than the InSci errors on all of these different data sets. And that the inequality constraint performance is significantly better. So you can convert each of these into a power measurement of 24 kilowatts versus 182 kilowatts if we don't use physics-informed rounding. We also see that for all of the methods, there's comparable performance across all the data sets on the dispatch error. Where we don't see comparable performance is on the inequality violations. And so across all the data sets, we see that the number of inequality violations are higher in data sets that are unseen, in particular for all three. And I want to note that the InSci methods perform equally poorly on all of the data sets on the inequality constraints. So then the next thing you might say is, okay, don't train on a perturbed data set, train on real low data sets. So that's what I've done. And the results are as follows. And what I really want to highlight on this slide is that when we train on realistic data sets and have representative load and generation profiles, we're able to get significantly better training performance. So we have 40% lower dispatch error, 95% lower voltage error, and a reduction by half in the number of inequality violations. And this is to say that we really need representative data sets. And so the data sets that I've generated as part of this project are an outcome of the thesis, in particular in the power systems domain where we don't have access to real data. And so these kind of data sets are really important for algorithm development, testing, and comparing across different methods. So one thing I hadn't talked about so far is the topology error, and I'm going to spend a little bit of time to explain what these graphs look like. So for each of the models for each of the architectures that I tested, I trained 10 independent models, and the distribution of topology errors is for each of those 10 models is shown here. So each of these box plots shows the topology error distribution over the test set for each of the 10 models that were tested. On all the previous slides, the results that I showed you was taking the average prediction across all 10 models in a very simple ensemble method and reporting those values. So if we do that again for the topology error, we see very bad performance in 40 to 50% range. However, if we consider the best performing model for both the InSci and the Cypher method, which we're trying to find that red bar, which is the mean as low to zero as possible, a low variance like we see here, and preferably everything's just kind of shifted to the lower end of that graph. We can reduce the topology error performance down to 14% with the Cypher model. So this means that on average, only 14% of the time do we get the optimal topology wrong. And this is a significant improvement in reduction. This 14% is actually comparable to the supervised methods on topology error. And so once again, the unsupervised approach is still able to perform quite well. If we look at what the topology error looks like during training, we do see that with the cipher and similarly the other physics-informed methods, we're going to see this kind of discontinuous or jumping behavior. And this would be expected because we're rounding to integer variables. And so you're going to have some of this discrete 0, 1 solutions happening. And then in comparison, the insight has a much smoother profile. But despite having that smoother profile, it's still not able to reduce the error very low because it's not able to commit to a topology. With the physics-informed rounding, a topology is selected at every point during training, upon which the physics-informed components will certify that our physical equations for our power flow are always satisfied. So,
very quick clarification
yes.
question. What's different from one model and the other?
So the initialization point, because there's stochasticity in how each of the neural networks are initialized. But the training data is the same as well as the test data, and the architecture remains the same across all 10 models. So in this chapter, I was answering the question of how we can efficiently keep lights on in a low carbon energy future. My proposal is that of using dynamic grid reconfiguration, and I've shown that this is able to reduce losses, improve voltage profiles across the grid, and increase solar utilization. To do so, we need the ability to make dynamic decisions, and for that, physics-informed machine learning really emerges as this prime domain to be able to make decisions that are optimal and feasible and are quick. And so to that end, I've proposed Grid Cipher, which is an end-to-end learning to optimize model that solves the dynamic reconfiguration problem. So now that we can efficiently keep lights on, how do we keep lights on steady? So if you've ever been in a room and the lights have dimmed or flickered very briefly, this might be the kind of phenomenon that I'm addressing in this chapter. So if we look at the future distribution grid, it can have a lot of different DERs. That includes things like flexible loads, solar generation, electric vehicles, and batteries. All of these devices give us the flexibility that we were trying to use in the earlier section in order to give us good, efficient performance. And they can similarly be used to answering this question, how to keep lights on steady. However, they do pose some challenges. So one of the challenges with, in particular, solar in the distribution system is that we get rapid voltage fluctuations. So what this looks like is, imagine you have solar panel, the sun is shining, it's generating some amount of electricity. A cloud comes over, very briefly blocks out the sun. The generation is going to drop very rapidly. And then when the cloud disappears, it's going to come back up very rapidly. That rapid change in generation also results in very rapid voltage fluctuations. And so if you have a large load that turns on, that might be why your lights dim very briefly and then come back, because for a moment, the voltage might have dipped a little too low below that lower operating point. And so we do have this challenge with more solar, but on the flip side, we can also use the solar to provide support throughout the grid if we can coordinate these resources in the right way. The second challenge is that when the sun is setting, we actually get this really high net load ramp that you can see that I'm highlighting over here. So the sun's going down, but everyone's still continuing to use the solar generation, still using load. And the loss of solar generation means that we have to meet generation somehow, and that's typically done with gas turbines that are very fast to react. However, gas turbines are very expensive to use, and on top of that, they are also carbon emitting. And so rather than using the gas turbine, we can think about using these different distributed devices to provide flexibility to the grid. The challenge that we have is that each of these devices are customer owned. So suppose you own an electric vehicle, are you going to give it to a utility company to use as however they want to manage the grid? Probably not. And so with our customer owned devices, we need to have a way that we can retain ownership of each of these resources, but allow for this decision making that can provide global support to the entire grid. And so my approach here is to use this physics aware distributed coordination architecture. I'm going to talk about the 3 layers from the bottom. The first is that electric grid layer, and here we're modeling the underlying distribution system, so we're always physics aware in our decision making. This is very similar to what we were doing in the prior section, where we had our power physics. The second layer is the device layer, and this is where all of our customer-owned devices will live. We know where these devices are located. We know what the flexibility they can provide. However, the challenge is that they are privately owned. And so to deal with that ownership boundary, we can introduce a communication layer on top. The idea here is basically that as individual DER owners, you will retain ownership of your device and autonomy in how it operates. You will make your own decisions subject to your preferences, but with a small amount of communication with your peers. Say you own an EV and you own a solar panel, with small amount of communication between the two of you, the set points that you can come up with in terms of how to actuate your devices will be able to provide services not only to the broader grid, but that are in line with your own personal preferences. And so you retain decision-making autonomy in this architecture. So upon this architecture, I've developed the two of the grid services to address those challenges that I mentioned earlier. The first is a voltage regulation service, and the second is a load ramp mitigation service. And I'm going to focus on the first one. So if we return to this concept of voltage regulation, which is where we want to keep the voltages within the tight bands required for operations, so that the lights kind of stay on steady, we can consider a distribution grid as follows. The way that voltage regulation is currently done in practice right now is using these typically mechanically actuated devices owned by the utility. So over here at the very head of the feeder, or the point of common coupling between the transmission and distribution system, we have what's called a load tap changer. And this basically helps to regulate voltages throughout the entire grid. So if the voltage is going to dip low at a particular point, then the load tap changer will change the tap setting to bring the voltage up across the entire grid. And if it's going to be too high, it can bring the voltage down throughout the entire grid. The challenge with this is that it has discrete set points. And because it's mechanically actuated, it also has slow timescales and degrades a lot for every tap change. And that high degradation comes with a really high cost. So what we want to do is we want to minimize or limit the number of tap operations that happen with the LTC. An emerging practice is to supplement the decisions made by the LTC with DERs or distributed solar, for example. And these devices, because they're connected with power electronics, have continuous dispatch, fast timescales, and then we can coordinate the resource response throughout the entire grid instead of having a particular location where the voltages are being supported. So we get global grid-wide support from the LTC and then distributed support from the solar resource. So similarly, voltage regulation can be cast as an optimization problem where we're trying to minimize the number of tap operations. And that's once again related to the degradation of those assets. And once we're able to do that, we also might want to keep a particular voltage profile V tilde. And this might be because the utility wants to operate certain devices in a certain way or to reduce the losses in the overall network. And so the utility might already know a particular profile that they'd like the voltages to follow. And so we also want to be able to minimize deviation from that profile. Once again, the set of constraints are our power physics and our devices, and this is very similar to what we had in the previous section. The only difference is that we've now added a load tap changer, which has those discrete set points. And so if we were to write this mathematically, we have the voltage at the PCC, pardon me, and that's where the tap setting is going to influence the voltage there. In terms of the power physics throughout the grid, we really care about the voltages in the network, and so we've pulled those out. We want to maintain those operating bands that I've mentioned, and then our tap limits means that we are once again dealing with a mixed integer optimization problem. So in order to address this, I'm introducing a bi-level optimization framework. If you think back to the physics-aware architecture, this is the electric grid layer that was at the very bottom. This is a device layer that was in the middle. And then the top communication layer is going to come in this bi-level framework as well. So the bi-level optimization framework involves an upper level and a lower level. At the upper level, we're looking at the PCC and the LTC that's located here. We want to actuate the LTC to minimize the number of tap operations and then support the voltages grid-wide. At the lower level, we want to use our distributed solar in order to provide a lot of that voltage support throughout the entire grid. And in particular, when we're trying to make this distributed decision, the solar is privately owned. And for that, I'm proposing the use of a distributed optimization algorithm or a pack-based optimization. So digging into what that looks like, the pack-based optimization algorithm looks as follows, and pack is proximal atomic coordination. So we have these different agents or atoms, and they coordinate with one another to make decisions. The equations are here, but rather than walking through the equations, I'm going to walk you through what it would look like in application. So suppose we have 3 different agents, and they're all individually privately owned. We have a flexible load, we have a solar resource, and then we have a storage device individually owned. So for each of these devices to retain autonomy, make their own decisions, but coordinate for global optimization, we can apply this algorithm. At the beginning, each of these device owners will prepare for optimization. What this looks like is forecasting load or generation and then any flexibility range. Once the optimization begins, it'll be an iterative optimization where at every step, the resources will optimize local decisions, some small amount of communication exchange, and then optimize their decisions again. And so by doing this repeatedly, we're able to get to a globally optimal solution that is able to support grid-wide voltages while still retaining decision autonomy at these agents. The information that's shared is just the local voltage at every node. And so there's no sensitivity related to that value. And it's something very readily shareable. It's just a single value. Once the optimization algorithm converges after multiple iterations, each of these devices know the optimal power set point for dispatch. And then we can update our inverters or our storage set points so that these resources then perform as decided by the optimization. So if we return to this bi-level optimization framework, we have the upper level and the lower level, which is what I just talked about here. And we can start putting everything together. So within our distribution grid, we have these different devices. We know the DER limits in terms of how much they can operate at a given time and their flexibility. We convert that flexibility range into a possible voltage range. So if these devices were to operate anywhere in this range phi t, then the voltages would be within these upper and lower limits throughout the entire grid. With information of this, at the upper level, the decision-making agent is going to decide whether that tap changer needs to be changed, the setting needs to be moved up or down. It can make that decision to support network-wide voltages. And then once that voltage has been set, that information is communicated to the lower level or the DERs. And the DERs will go through that pack-based optimization, come to the set point, and inject back into the distribution grid over here. Now, this kind of architecture is something that you might see in literature with slightly different functions on some of these different levels. But what's really missing is more coordination. So I've talked a lot about the coordination happening at the lower level between these devices. But if you look at the upper and lower level decisions, there isn't a lot of coordination being made, and there's no amount of co-optimization that's happening. And so my proposal is to add another layer of coordination so we can move towards this co-optimization framework. So when we talk about this upper level decision-making agent, it has two decisions it can make now. The first is the same, where it decides whether it needs to change that tap setting or not to bring all of the voltages up. And the second decision is asking the DERs to restrict where they can operate. So suppose you have a solar generator. It can, suppose at a given time, it can inject anywhere between 8 to 12 units of power. In order to maintain grid-wide voltages, it might be better for that solar generator to only inject 10 to 12 units of power. And so that decision can be made over here to limit the number of tap changes. We can leverage the flexibility of these DERs to still stay within their desired operating range or their flexibility range, and then come down here with that new operating range and make the decisions with the pack algorithm again. So this kind of coordination allows us to really leverage the flexibility of DERs and move towards solving this larger optimization problem in a coordinated fashion. So I've run offline simulations of this proposed framework on a real utility feeder. It has 56 nodes and about 20% penetration of solar generation, which is very typical to the test cases that I introduced earlier. So we're trying to limit the number of tap operations, and we're trying to maintain a profile of 0.97 voltage throughout the entire grid. And this was what the utility wanted us to do. I've looked at 3 different simulation test cases. So the first is where we don't have that upper level. We're only using the bottom level distributed coordination. The second is where we have both levels, but not that additional coordination. And then the third is where we have my proposed method with both levels and the additional coordination mechanism. And the results are as follows. There's 2 things I want to highlight here. The first is that without the LTC looking at network-wide voltages, we see significant voltage violations, particularly in the evening when the load is high and solar generation is no longer available. So DERs alone are not enough to support the voltages throughout the grid. And instead, we need to rely on some of these older utility practices augmented with additional DERs. So then if we consider where we do have the DERs and the LTC, but without my proposed coordination, we do get better voltages, so we don't see violations, but we do see a lot of tap changes that happen here. So let me just quickly jump here. Without coordination, we see 4 different tap changes throughout the day. And with my proposed coordination, we only have one. And that happens just at the beginning of the day because the tap was set to a neutral position of 0. So it's basically going up to this tap setting of 4. And it's very likely that for a long duration of time, it's going to stay at that tap setting of 4 as well. The other nice thing is that we're better able to regulate about that 0.97 band, which is roughly about here as compared to the blue. And that means that we also see lower network losses throughout the entire grid. And so it's not only able to keep lights on steady, it's able to do it more efficiently as compared to other methods as well. So that was the first service. And I did mention the second service. I'm not going to present it in detail, but I just want to give you an idea of what this one looks like. So what we're really concerned with is this steep ramp that's happening over here. And that happens for the net load. And that happens as the sun is going down. And so if we look at distributed coordination instead of local approaches, we can reduce the ramp down to this yellow line as opposed to the red or blue. And by shrinking that or making it shorter, that ramp, we're able to reduce not only the ramping needs, but also able to reduce the amount of gas turbines that are used in order to supply our load. And so in this chapter, I was asking the question of how we can keep lights on steady in a low carbon energy future. My proposal is to use flexibility from DERs, but in order to do this, we need to have decision making across privately owned devices. And for this, I'm proposing the use of the physics-aware distributed coordination architecture and the following services that are built upon the architecture. So I've done a lot of work in my time here at MIT answering this question of how we can keep lights on in a low carbon future, but unsurprisingly, there's still a lot more work that can be done and a lot of really interesting research questions. So I've put a couple of them up here and I've kind of binned them into these two. So the first is whether machine learning can be used to realize flexible and dynamic decisions for more than just dynamic reconfiguration. So one question is whether we can generalize to grid topology. So can we start using graph neural networks in order to do this? The other is looking at different operations in the power systems. And so perhaps we're generalizing to a family of rounding functions and creating this more general framework for the grid cipher. And then lastly, as I mentioned, those open source data sets are really important. And so continuing to collaborate and develop really representative data sets so we can understand the behavior of our algorithms on real systems without actually needing to deploy on real systems first. The second set of questions are looking at deploying distributed intelligence in the power systems today, as opposed to 10 years in the future. And so one of the challenges is scaling up our algorithms to millions of devices. So because they're iterative algorithms, they can require sometimes thousands of iterations to converge. And so accelerated methods is something I worked on and collaborated on during my time here at MIT, but there's still a lot more work that needs to be done to make those methods viable. The second is looking at secure operations. So can we make all of these distributed methods cyber secure? So the second you start introducing more intelligence, you have to ask this question of cybersecurity. And last, we can start coming back to this domain that I presented here of blending data-driven and model-based approaches. So where are the places that we can really blend these methods together for decision-making in power systems? So during my time, I've published the following journal and conference papers on a couple of the different projects that I've worked on. And in the time that remains, I just want to say some thank yous. And so starting with the funding acknowledgements that I had, funding that I've had. So I've had